Hi, my name is Jef Laga. I'm a postdoc at the University of Cambridge, and together with my collaborators Ciaran Schembri, Ari Shnidman, and John Voight, we wrote a paper entitled Rational Torsion on Abelian Surfaces with Quaternionic Multiplication, and it just got published in Forum of Mathematics Sigma. The purpose of this very short video is to give you a quick introduction to the main players of the paper, and hopefully that will pique your interest and you would like to read it. Okay, so to motivate this, let E over Q be an elliptic curve. So this is very well-studied objects in number theory and algebraic geometry. These are exactly genus 1 curves over Q with a distinguished rational point. Then their group of rational points is a finely generated abelian group, and their torsion subgroup is a finite abelian group. And Mazur, in the 70s, in his Eisenstein ideal paper, classified exactly all the possibilities that this torsion subgroup can take. So Mazur showed that the torsion subgroup is one of the following 15 groups. It's either cyclic or Z mod 2Z times a cyclic group. And in each case, you can give a rational parameterization of all the elliptic curves that have such a torsion subgroup. And so this was a monumental achievement of arithmetic geometry of the 20th century. But generalizations so far have resisted many attacks. The most natural generalization would be, what about higher dimensional abelian varieties? So elliptic curves are abelian varieties of dimension 1. So it's very natural to try to look at abelian surfaces, for example, two-dimensional abelian varieties. But even there, our knowledge is very sparse. It's a completely open question because, for example, we have not excluded any prime occurring as the torsion subgroup, the torsion order of a rational torsion point on the abelian surface. So here's a question that's, to date, to the best of my knowledge, completely open. Is there a prime L such that no abelian surface over Q has L dividing its torsion order? So for example, we do not know whether there exists an abelian surface with this torsion group of order divisible by 691. So since it's very hard to say something about a general two-dimensional abelian variety, we will restrict to abelian surfaces with many endomorphisms, which are much easier to study because they have additional symmetries. So the principal object of study will be a PQM surface. And just for ease of exposition, this definition is slightly different from the one given in the paper. So if you want to look at the details there, then by all means have a look. But for this presentation, a PQM surface will be an abelian surface over Q, such that its geometric endomorphism ring, which is the endomorphism ring of the base change of the surface to Q bar, is a maximal order in a non-split quaternion algebra B. So PQM is an abbreviation which stands for potential quaternionic multiplication. And it's quaternionic multiplication because it involves quaternion algebras, and potential because you have to pass through the algebraic closure of Q. And this non-split condition is the same as saying that B is not isomorphic as a Q algebra to 2 by 2 matrices over Q. And this actually implies that PQM surfaces are always geometrically simple. They're not isogenous to a product of elliptic curve, even if we pass through in a field extension. And this means that the study of PQM surfaces does not reduce to the study of elliptic curves. So there's a genuine two-dimensional phenomenon going on here. But one reason that they're maybe easier to study is because they're moduli spaces. Once you fix additional data like polarization and the fixed order in a fixed quaternion algebra, their moduli spaces are one-dimensional. So PQM surfaces are, roughly speaking, parameterized by rational points on Shimura curves, which makes them perhaps similar to elliptic curves, which are with level structure, which are parameterized by modular curves. And so this is our object of interest, and our main theorem constrains the torsion subgroup of such a PQM surface. So here is one way of stating it. And again, for more details and a more detailed explanation, I refer to the paper. Then, so here's the theorem. So suppose A over Q is a PQM abelian surface. Then the torsion subgroup, which I remind you is a finite abelian group, is, in this case, 12 torsion. So every point has order dividing 12. 12p is 0 for every p in the torsion subgroup. It has cardinality at most 18, and it's generated by 3 elements, at most 3 elements. Okay, so these are the constraints we managed to prove for this class of abelian surfaces. So let me provide some remarks to this theorem. So the first part implies that there is no L torsion for all primes at least 5. So there's no 5 torsion points, no 7 torsion points, etc., etc. So this is even stronger bound than in the Mazur case. So the torsion subgroups, PQM surfaces, is very constrained. And if you do the group theory, or look at all fine abelian groups that satisfy these three conditions, then actually we get 14 groups satisfying these three conditions, but we can only realize 6 of them. We can realize them infinitely often. So it is still an open question. This is an open question of our paper, whether the 8 remaining groups can be realized or not. So most notably, we do not know whether Z mod 4Z occurs. So we do not know whether there exist points of order exactly 4 on PQM abelian surfaces. On the other hand, we do have a complete classification when we impose additional conditions on A, namely when a part of the endomorphism algebra is defined over Q. So when the endomorphism ring over Q is an order in a real quadratic field. And in that case, we can use additional arguments using modularity, for example, to more constrain this case more and have a complete classification. Okay, so that's the theorem. And let me sort of say one line about the proof or the ingredients that go into the proof. So the proof is a combination of algebra, arithmetic, and algorithms. So the algebra part is the quaternion arithmetic that goes into play. So this is explicit calculations in orders in quaternion algebras. And these are more difficult than, say, analogous calculations in fields because the quaternion algebras are non-commutative. On the other hand, we also exploit the structure of neural models of PQM surfaces and analyze what happens when you take a torsion point defined over Q and reduce it modulo P, even when you have a prime of bad reduction. And the role of additive primes, so primes of additive reduction, play a very important role in the work of Lorenzini regarding this. And in the GL2 type case, we use the modularity of abelian surfaces of GL2 types, so the connection to modular forms, to further constrain the possibilities. And on the algorithmic side, we use various data from the LMFDB, which is an L functions and modular forms database concerning modular forms and abelian surfaces over finite fields in the form of Honda-Tate theory to further analyze our class of surfaces. Okay, so I hope this very short presentation piqued your interest, and I encourage you to look into the paper. Thank you for listening.